Hi, welcome to the latest episode of Math Talk. Before we dive into today's wonderful episode, I just want to point out, as you'll notice, there were some technical difficulties with the video equipment, unfortunately. So, basically what that means is there's certain times when the video would blink sort of on and off, creating a very strobe-like effect, which could be quite distracting. So in order to mitigate those effects, there are certain stretches, some are very short, some a little bit longer, maybe a minute or two at a time, where the screen will just be a frozen image because I decided to replace it with that frozen image instead of just having it flash on and off the whole time. But thankfully, it seems like the audio all turned out fine, which is the most important part. So you might just want to listen to this one as a normal podcast, but I think for the most part, the video should be fine as well. I just wanted to let you know about that ahead of time. Thanks so much for tuning in, and enjoy the episode. So, we're back with a new episode of Math Talk. I'm joined today by a very special guest, Professor Joe Silverman, who has had a very long and successful career in arithmetic geometry, broadly speaking, but of course with specialization in topics including elliptic curves, arithmetic dynamics, and also, elliptic curves as related to cryptography. And of course, as many of you will know, he's the author of several quite famous textbooks in the field, particularly on elliptic curves. So thank you very much for joining me.
My pleasure.
So first, I'll ask what topics are on the top of your mind today, these days.
In terms of research, I've mostly been doing arithmetic dynamics recently, especially distribution of orbits, sort of arithmetically and algebraically on varieties.
Right. Yeah, looking forward to hearing more about those tomorrow.
Mm-hmm.
And so, as I usually like to kick things off, head all the way back to the early days, how you first got interested in mathematics, or when you first realized that you were interested in mathematics. If there was any stories or people or books that you found particularly inspiring.
I was always interested in math, and I have an uncle who's a physicist, so I kind of was always aiming toward math or physics. And when I got to college, and actually freshman year of college, I had a superb physics teacher and a so-so math teacher, and at the end of the year I was still more interested in math, so that's when I decided I was more interested in math than physics. Books, these are all things. Isaac Asimov, the science fiction writer, actually has a number of books with essays about math and chemistry and physics and stuff. I found the math in those fascinating. There was an older book by George Gamow called, I think, 1, 2, 3 Infinity, that was similarly had essays about math aimed for the general public, which were comprehensible to a high school student.
I see. So that was, I guess, early days of university. And then as you progressed in your university education, was there a particular, in your undergrad, did you start to develop a bit of a specialization or a taste for certain areas?
No, not really. As an undergrad, I thought I was more interested in analysis, because algebra seemed more tricks than a coherent theory, which it does, I think, at the beginning.
Interesting. Because I feel most people have the impression's the opposite, or at least that's my impression. But
yeah. But then as I learned more algebra, I got more interested in it. And by the time I got to grad school, I was sort of aimed in an algebraic direction, either number theory or algebraic geometry or something along those lines.
Right. So then, Tate was your supervisor.
Mm-hmm.
Did you already? I guess so. So, by the start of grad school, you had a mind towards algebra at that point. But did you already know that you wanted to work with him specifically, or so you just sort of went there, started taking courses, and connected with him at some point, or?
Yeah. Well, I took algebraic geometry, I think 3 times. Hironaka taught it once. It was super algebraic. David Giesiger taught a much more sort of down-to-earth, more geometric version. And actually, there wasn't an algebraic number theory course taught at an appropriate time for me to take it, so I kind of studied that on my own and worked with some of the other grad students. Then Sayre came and gave a topics course on Diophantine geometry, basically arithmetic geometry, that I really found interesting. And yeah, I decided to try to work with Tate. Tate had a reputation of, he basically didn't propose problems. You needed to go to him with a problem. So during Sayre's course, Sayre had mentioned a couple of conjectures that Serge Lang had made that seemed interesting. So I went to Tate and asked if they might be a reasonable thing to work on for, a thesis problem, and he said okay. So I started working with him. That was, I guess, the middle of my 3rd year in grad school. And then my 4th year of grad school, Tate was in France the whole year, so ended up, Barry Mazur was sort of a surrogate advisor. He was very nice about listening to me.
I see. Yeah. Did you, were you still at least corresponding through letters with Tate at that time?
Yeah, to some extent. I sent him some letters. I got 1 or 2 from him while he was there. I really got to start talking with him and meeting with him when he got back during my 5th year of grad school.
Yeah. So we were actually, when we were at dinner last night, we were talking a bit about letters and the fact that today you can send a Discord message and then instantly, or an email, and you realize immediately that I made a mistake, and you can correct yourself, or you realize it's obvious a moment later. But back when you had to write letters and wait for a while, but I think you mentioned something about waiting a day to see if there was a correction letter following up, or for writing a joint paper with someone. Right.
It was a good idea to do that.
Right.
Yeah. With Tate, I did send him probably a number of longish letters, but they were more designed, to figure out what I was doing, for me to figure out what I was doing, as much as to tell him what I was doing.
Right. Just the classic sounding board of, sometimes all you need to do is try to explain it to someone, and through that explanation, the light bulb goes off. Yeah. Okay, so then, and then was your 5th year was your final year of your PhD? And then I'm guessing you went through a couple postdocs at that point in time, or?
Just one. Yeah, I got a postdoc at MIT, so a more instructorship, which at the time were 2-year positions. But after my 1st year, I applied and also got an NSF postdoc, which was a 2-year thing. So between them, it ended up as a 4-year position at MIT. So that was really nice.
Yeah, that's nice that you can be there in one place. I think there's a lot of people these days that have to do a bit of a moving around, which is nice in its own sense. It's nice, I think, to see the world and stay in place. But
it is. I had another constraint. I was married by that point with a daughter. So my wife's an actuary, so she was working at John Hancock in Boston, and we were not looking to move if we could avoid it.
Right. Yeah, certainly. Yeah. So, in your postdoc, then, how did your what were you working on in your postdoc? How did your research evolve over over the course of your postdoc? Like, were you picking up different things at that time, or were you just sort of drilling down deeper into certain aspects?
Yeah, I think I was more trying to expand than drill down. I mean, I wrote up the stuff in my thesis and tried to expand on it to some extent. The big expansion came a few years later when I met Mark Hindry at a conference, and we sort of started working sort of on another direction of one of the topics of my thesis.
How did that come up? Like, had you just given a talk at the conference about some topics from your thesis, and he was like, "Oh, that's cool, I want to work on it," or how did that collaboration actually come to play?
That's a great question. No, I did give a talk, actually, about a conjecture I'd come up with that I talked about yesterday at Renata's seminar, but that was not at all this Lang-Height conjecture that Mark and I ended up working on. Yeah, that's a really good question. I don't remember. Somehow, I mean, at big conference, people chatting, and
right.
Somehow it came up that I'd worked on this, and Mark was interested in it, and we started batting ideas back and forth.
Right.
And then, interestingly, on the flight home, I had an idea, and I sort of scribbled it down. It turns out Mark had a similar idea, and it was a great collaboration. But I don't remember how it first came up when we were chatting.
Yeah, I'm always curious about that. The process of collaboration. I mean, I've had some collaboration so far, but it's very limited. I'm still early in my career, so I'm trying to keep in mind what are ways I can help generate collaborations, and of course going to conferences and talking to people is probably number one.
I mean, nowadays there are a lot of conferences that are designed to create collaborations, like AIM.
Right.
Is designed to put together groups to do research projects and things like that. Yeah. And
the point about the plane, I also I'm guessing you're someone who works well on planes. No. Oh, okay.
No. It's just I was excited about what we'd been talking about, so I managed to.
I see.
No, well, trying to think back then, whether they had how good the movies were. I mean, nowadays, I see a flight is a good time to binge watch movies.
Right. I found for myself, well, I guess these days I'm paying for the cheapest flights possible, so a lot of them don't have the movies on it. So when they don't, I find that I'm very, very productive on planes. In fact, I'm probably more productive on a plane than anywhere else, because I'm just sort of confined to this box, and I've got my notepad, and it's so sometimes it's a blessing for getting work done for myself personally. Unless there's chess on the plane, then. Yeah. So
I was going to say, I have one colleague who looks at flights to conferences as the time to start preparing his talk. Another thing to do.
That's cutting it a little close for myself personally. But
yeah, me too.
Yeah. Okay, so where were we in the progression of things? We had postdocs, and we were talking about the evolution of your postdocs. So then, when it came time for your professorship. Oh, I guess I should also ask about at this point in time, the writing of of your various textbooks, where this falls in the timeline.
Okay, yeah, I was going to bring that up if we were going to move on. Yeah, the first book was written while I was a postdoc at MIT.
Right. And this was arithmetic?
This was the arithmetic of elliptic curves.
Yeah.
That rational points book with Tate was much later.
And so when was like, when did you think, oh, I can write a textbook, or I'm going to write a textbook? Like, were these notes that slowly built up over time, or did one day you just sat down and said, you know what, someone needs to write a good textbook and it's going to be me? Like, what was the whole thought process behind how that started?
Yeah, to a large extent it was serendipitous. So here's what happened. MIT very nicely, for the more instructors, they let them teach a one-semester topics course in anything they want. So I taught a course on the arithmetic elliptic curves, which was the title of an article Tate had written for Invenciones, which was a survey article, but was sort of the best source for getting the main facts. They didn't have a lot of proofs or anything, maybe 10, 15 pages. It's a beautiful article. So I took that article and expanded it, putting in proofs and stuff, and taught this course, and had, I don't know, maybe 100, 150 handwritten pages of course notes, which I mentioned to someone I knew named Gary Cornell, who had been a grad student at Brown when I was an undergraduate, so I knew him from that. I knew he had some publishing contacts. And said, well, I taught this course, I have these notes, you know, maybe someday I'll think about turning it into a book. So Gary knew the main mathematics editor at Springer in New York, whose name was Walter Kaufman-Buehler. And he mentioned this to Walter, and Walter sent me a letter saying, I hear you're writing a book, would you be interested in publishing it with Springer? Could you send me some material? So I sent him, I don't know, maybe the proposed table of contents and a couple pages of description of what would be in it, and he sent me a contract. So
obviously liked what he saw,
I guess, and possibly Gary said some nice things about it. But there's also back in the days when when an editor could basically just decide on a book without running it through committees and things,
which is not the case today.
Not anymore. The process is more complicated, and they'd certainly want to see a few typed chapters and things like that.
Right.
So I said okay, and I figured with these pretty elaborate notes and stuff, how long could it take? A year, maybe? So it took 3 years.
Right. I was about to say, it's never, yeah.
And of course, this was back pre-tech. I mean, I hand wrote it. A secretary at MIT typed it, typewriter. Then went through some sort of editing stage. Then it went to typesetters in Hong Kong. And then the galley proofs came, and those were copy read and edited. Then it went back and was page proof. So big long process. Anyway, so that's how the first book came about.
Oh, excellent. Yeah. And so then, so back to your early career. So at this point, had you mostly just been working with elliptic curves? Like when, for example, did some of your interests broaden to include like arithmetic dynamics? Or
that was significantly later, and a whole story in itself. I continued working with elliptic curves, but also sort of more general arithmetic geometry, just solving Diophantine equations, polynomial equations, and integers or rational numbers. Other curves, higher dimensional varieties, unit groups, things like that. That's pretty much what I was working on until this arithmetic dynamics stuff came up.
And I guess one thing that's maybe a good thing for myself to start thinking about, if all my postdocs go well, is your sort of first experiences as a supervisor. like, what was the learning process for you, learning how to supervise?
Yeah, I mean, I think everyone has to develop their own style. Tate was very happy to talk to his students, if they went to him and said, "I want to talk."
Right.
But he didn't schedule regular appointments or anything. I kind of went the other direction. I meet with each of my graduate students every week, pretty basically, for 45 minutes or an hour. And I find that works well for me. And we don't have to, I mean, not everyone, you can't make progress every week, but that's fine. You just chat about what you were thinking about, or sometimes we just chat about other mathematical things.
Right. And so when you have several grad students, are they usually working on fairly different things, or have there been times where the projects have intersected and like dovetailed with each other, or how does that usually go?
My preference is for the projects to be reasonably separate.
So people aren't stepping on each other's toes.
So people aren't stepping on each other's toes. In particular, something which I haven't had but would be a slightly nightmare situation would be, two students who have worked on closely related projects who finished the same year, and now you're writing letters for both of them.
Right.
And hiring committees are going to take the letters and compare them line by line.
Right. Yeah.
Yeah.
No, that makes sense.
Yeah. Having said that, I mean, my students work in arithmetic geometry or arithmetic dynamics mostly. So, there's some relations.
Right. So, yeah, speaking of so I am curious about when the arithmetic dynamics did start to come up, which you mentioned later. And you did also mention that the book with Tate came much later. Were there other books in between that? So arithmetic was first, and then was advanced topics second?
I think so.
Okay.
Yeah. The book with Tate, Tate had given a series of lectures at Haverford College. So this was to, math major undergraduates on elliptic curves. And someone had typed up the notes, and first they were mimeographed, which I'm going to try to describe it. If you look up what a mimeograph machine was, it was predecessor to Xerox machines, to copy machines, and they were being passed around, those notes, and then Xerox machines became available, and people started Xeroxing the mimeograph and Xeroxing the Xeroxes of the mimeographs, and they became less and less legible.
Right.
And I was teaching the second semester I was at Brown by this point, teaching the undergraduate algebra sequence. And the second semester, pretty much always, is Galois theory and then some other topic. So I said, well, I'll do Tate's notes. And I asked Tate if it was okay to retype them, in, I want to say LaTeX, but actually it was plain tech at that point. And, to distribute them, and Tate very graciously said, sure, that'd be fine. So I did that. And having done that, maybe a year later, I guess, I asked them, would you be agreeable to me writing a few extra chapters? And then we turn it into a book and see if maybe Springer's interested. And he said that sounded good. So, as I was mentioning at dinner last night, I think the best books are books that have an author's voice.
Right.
But in this case, it wasn't sort of co-authoring each chapter. The first half of the book, pretty much, is Tate's voice. I did some editing to turn what were lecture notes into a book, but and the second half of the book is my voice, because I wrote that. And Springer was very interested. But by that point, I mean, Walter Kaufmann Buehler, who I mentioned earlier, he died he was in his 40s, I think. It was very tragic. But the new editor there was interested. And so we did that, and then Tate said, there should really be an appendix developing intersection theory so that we can actually prove the associative law for the group law on elliptic curves. I said, great. So he started writing that relatively slowly. I mean, Tate was definitely something of a perfectionist in terms of writing.
I see.
But it finally got done. Anyway, so that's how that book came about.
Very cool. Very cool.
Yeah.
And yeah, so when and maybe how did the arithmetic dynamics start to come about?
Okay, so that was another bit of serendipity, which is why I always advise my students, go to talks even in fields especially colloquium style talks in fields you don't know anything about. So there was an AMS sectional meeting at Union College, and one of the special sessions was number theory. I'd been invited to give a talk, and interesting talks, great. They'd invited John Milner to give sort of the big plenary talk on complex dynamics. Because Milner started as a topologist, but he then moved on. He did a lot in dynamics also. And my knowledge of complex dynamics was zero. I had never seen anything. And so I went to this talk, and the first half of the talk, it was beautifully organized, and he gave a summary of one-dimensional complex dynamics, basically starting with Fatou and Julia, and early 20th century, maybe even a little earlier, and working up toward modern-day complex, one-dimensional complex dynamics. And almost every theorem he stated, I was thinking, there's sort of an analog in that if you think about the statement of the theorem, but think of it as in arithmetic geometry terms. So he was talking about orbits of points that, you take a point, you apply a function, you get an orbit.
Right.
This is discrete dynamics. And one interesting class of points are the ones that loop back on themselves, so finite orbits.
Right.
Pre-periodic points.
Right.
And those were clearly analogous to points of finite order on elliptic curves.
Right. Right.
And orbits that didn't loop back on themselves were the analogs of points of infinite order on elliptic curves. I mean, at this date, I don't remember the other analogies that came to mind, but there were all these interesting things. So that's why I kind of got started thinking about it. And actually, the next day at breakfast in the cafeteria, I saw Milner. He'd sat down at a table, so I went over and introduced myself. And I asked him what, in retrospect, were some incredibly naive questions about dynamics. And he was very, very friendly and helpful and encouraging. And I later met him, I've met him a number of times, a wonderful person. So anyway, that was the start of it.
So anyways, that's a great piece of advice then, I think, to always go to conferences, even if you know zero, because then you might end up doing a bunch of work in that field.
Well, but the other thing is, look for analogies.
Right.
I mean, I would say a lot of my career has been based on looking at articles and thinking of analogous things that people tend to think that what they know, everyone knows, and it's not true.
Right.
What you know is different from what they know.
Right.
And they may know a lot more than you about what their field is, but you can have your own perspectives.
Right. Well, it's very interesting. I was thinking about this earlier. You mentioned the fact that you had taken algebra several times.
Algebraic geometry.
Or algebraic geometry several times, and with these different perspectives, with I think you mentioned on the train yesterday that Hironaka was like totally algebraic, and I mean it's interesting, we normally don't think about taking the course several times. I mean, of course, it happens to a lot of people. You especially if you're doing a master's in between, sometimes you end up having to take these courses in between. But I guess I've always been thinking about reaching for a lot of breadth in my courses. But I guess, with that comment with what you mentioned about taking different versions of algebraic geometry, and now this comment about having different perspectives is just making me think about the value of taking the exact same course but with different people to pick up on those minor differences, those or major differences even, and ways of thinking and conceiving of the subject.
Yeah, I mean, there's a limit. There's not unlimited time, so
right.
You want to try not to do the same stuff overlapping. Yeah. But especially in a field like algebraic geometry, where you can approach it sort of from the geometry, but with algebra side, or really commutative algebra side, or from the complex analysis side. I mean, reading Griffiths and Harris's algebraic geometry book and reading Hartshorne's book, it's like it's not two different subjects, it's the same subject, but they're coming at it from such different directions and perspectives. Right. And the tools you get are very valuable. Right.
And on the point of analogies, there is, I'm sure this famous quote. I forget who it's by, but it's something to the effect of, good mathematicians see analogies, great mathematicians see analogies between analogies. Yeah. I always liked that quote. Yeah.
It's a good quote.
Yeah.
I've forgotten who said it also.
Yeah. I do have it. It's on my personal page if people want to look it up. I'm very happy about my math quote collection that I keep there. So yeah. Okay, so maybe I guess we can turn it to some of the viewer questions. There's I think a couple ones that that I looked at. Although you did mention, some of them were strange or maybe a little unrelated. I think I am curious. Someone had asked about, I somewhat jokingly, I think about the significance of the number 67 in your field, and I have
no idea what they're
okay. I was wondering because there's this joke about 57's the Grothendieck prime or something, so I thought maybe there's some joke hidden there. I don't know.
I don't think so.
I don't know. Okay. So I guess we can. Well, I think this is maybe. I mean, you can tell me if you're not that interested in the question, but. Your perspective on how academia or math academia in particular has changed from when you were a student to today, and what changes you would make, if any.
Could probably get in trouble with that one. Changed. I mean, academia as a whole, or math, there's a lot of perspectives there.
I guess whichever one you think you have something to offer on.
Yeah, I mean, students are students. They always have been. They always will be, I think. Math, I mean, the way math's done has certainly changed, partly because of the internet.
Right.
Even the introduction of LaTeX suddenly meant that people could write their own papers. And
right.
See, I mean, if you had to handwrite a paper, have someone type it, and then it got sent off to a journal, and if you wanted to distribute copies, it was difficult to type it up yourself, put it on the archive, and submit it.
Right.
Makes for a very different process. It speeds things up.
Yeah.
It's much easier to find out what's being done, again, because of the archive, rather than going to the library every month and skimming the titles of all the articles in the journals, which are already a few years out of date.
I wonder if back in the day there was a lot more collisions of people like simultaneously publishing, or people publishing a result that had been proved a year or two before. I don't know if you've noticed any of that, but I could imagine, because it would just be harder then to maybe keep track of everything in all the journals, whereas now you can just do a Google search.
Well, yes and no. That certainly did happen a bunch. I don't know about actually publishing, but someone would work on something and then discover that it had been done a few years earlier.
Right.
Actually, I'll give you two examples of that in a second. The flip side is that now there's a lot more math out there being written, being published, so it can be hard to know exactly what's buried, as Proposition 23 in one of the 50 papers that have been posted on the archive in the last 2 years.
Right.
And it's also a little hard to search for that, even with internet tools, especially because you can't search an equation so much.
Right.
AI may actually make that easier.
Yeah, I think that combined with Lean or these proof assistants, I think people are hoping that it might make, if there can be some sort of, big theorem or equation database or something, it might possibly be easier. But
possibly, but if you're proving a theorem that's basically this complicated equation, and that equation's already out there, but with different notation and stuff, the matching's not so easy.
Right.
I had an experience in grad school. One of the it was postdoc. One of the other postdocs and I at MIT decided to work on this. It's called the. I can't remember the term. Anyway, it was something about elliptic curves. And we came up with this very nice proof, and it was a great collaboration. The proof really had two key ideas to be worked out, and we each did one of them, so it was great. And as we were writing it up, my co-author was browsing through the MIT library journals and discovered that, about, 10 years earlier, Steve Lichtenbaum, who's a very good mathematician, actually ended up as a colleague of mine for many years too, had published a proof of the exact theorem we were proving. And when we looked, his proof had the exact same two steps with the same, and more or less the proofs that we had rediscovered. So that became unpublishable, which is a shame. Yeah. And that, you're right, we probably would have been able to discover with modern search tools.
Right.
Oh, it was the period index problem for elliptic curves. When I was in grad school, a more frightening thing was one of the, I guess no problem mentioning them, one of the people in my class, Dave Beyer, who's now a great geometer, had been working on a problem and he solved it, and it was going to be a very nice thesis, and then his advisor discovered that someone had published the proof just a few years before. And again, that probably could have been discovered with modern tools, but
right.
So he rather frantically worked out another theorem, another proof, and graduated in time. And he's done very well. In fact, he and Mike Stillman were the original people who developed the computer algebra system Macaulay.
Okay.
Which you've probably heard of.
Yes,
David's a professor at Barnard, has been for his whole career. So it didn't damage his career or prospects or anything. So it has a happy ending, but it was certainly a frightening thing to happen.
I mean, it definitely is a frightening thing, but maybe you have something to offer on this, because I've definitely had conversations with people before where they're concerned that someone's beating them to a result, or that same result is being published around the same time, even within a year of each other. But, as much as that kind of sucks, especially if you're the one that's publishing, a little bit after, my thought would be that a lot of mathematicians just understand that this happens and that's how it goes. So I don't know what your impression is of that is like if you're on a hiring committee, for example, and you see, or for postdocs or permanent positions or whatnot, what your impression of that is, and also what you think the impression of that is more generally. How damaging do you think that really is? I mean, of course, it's something to avoid, but
yeah, I mean, if it's that people were doing the research simultaneously, and then one of them happens to publish it a little before the other, I personally think that's fine. I don't. I think everyone who did that deserves credit. Also, usually even if they're proving the same result, the proofs aren't quite the same. The perspectives are different. I mean, there's usually a really good. So I think that's okay. I mean, I've certainly also. Well, actually, this happened recently. I was doing a joint project with Nicole Looper, and someone else was also doing it. And we put papers in the archive at more or less the same time. We'd been doing research about the same time. And it was mostly the same theorem, but ours was stronger in one way, but the other person's was stronger, actually in a couple of ways, I would say. So what we ended up doing was we corresponded back and forth, and should we each submit separately? But we ended up saying, let's combine the papers and prove something that has all the strengths. And that's what we did. So it ended up as a 3-person paper. So that also can happen. Yeah. I mean, no one was trying to say, well, I'm going to get my paper published first.
Right.
There's also the issue that if I submit my paper, on a certain date, and someone else submits their paper to a different journal a year later, their paper might appear first, because the refereeing and publication process, it can take a year, it can take 3 years.
Right.
It can get, the first paper submitted can get rejected and have to be resubmitted elsewhere, because it's always a crapshoot whether it's accepted or not.
Right. But I mean, that's also the value of archive, because the preprint, you've got the date of your preprint.
That is true.
Yeah.
That's true to some extent, though it also sometimes means people rush and put something on the archive that shouldn't really be there.
Right.
It's not quite ready.
Right.
Yeah.
I guess that's sort of something I'm thinking about at the moment, actually, because I have a paper that's very near completion, and of course it's postdoc season, so I'm tempted to get it out as soon as possible, but there's like one section I'm rewriting right now, and in the back of my mind, part of me is like, oh, I shouldn't be rewriting this. I should just get it out so I have another paper. But then there's another, there is a part of me that's like, well, but I know in my heart that I can do this section better. It's not that it's wrong necessarily, but it's just, I know I have something better to say about this section. So that's, I don't know if you have any perspective on that, but that's
it's you got to decide yourself, case by case.
Yeah.
The one thing not to do, which some people do, is, I mean, any paper, you can always do more work on it. I mean, a good paper always raises more questions. You can always simplify it. You can always do whatever. At some point, you have to sit down and it's done. Send it off, and then there'll be another paper if I do more. But improving the result in the section and making it better written, that's usually worth doing. On the other hand, job market, postdocs, all that kind of stuff, that makes a difference. At least we don't have the computer science model where most of the publications are at conferences, and the deadline for submitting to the conference, they cut off they close the server at midnight on whatever date, and if you get it in or you don't get it in.
I see.
Yeah. That really encourages submission of not quite finished stuff.
Right. Well, I'll be wary. I'll be wary of that. Yeah, it is a good thing we don't have that system. Well, I guess So I guess we've already talked about the writing of the books. Right. You mentioned this is also a strange question, right? Areal Galois theory, or
yeah. Well, there's a question about arboreal Galois theory and
post-critically finite maps.
Post-critically PCF maps. Yeah. I mean, the arboreal, it's. I mean, discrete dynamics. You take a point, a function, you see where the point goes, right? Or you can take the point and take the inverse images. So you take a point, its inverse image might be 3 points, the inverse image of those reach 3 points. So you get a tree.
Right.
Which potentially could have loops, but say it doesn't. And studying the number theoretic properties of those points, because if you start with a rational number, say, and a rational function, or polynomial even, if you push it forward with the function, you'll get all rational numbers. But the inverse images will be in number fields, in finite extensions of Q. So you can ask about the fields they generate, Galois properties. Anyway, that's what arboreal stuff is. And it's actually not a part of arithmetic dynamics that I've done that much with. The name, by the way, is due to Nigel Boston and maybe Rafe Jones, which I really like, the arboreal for tree, as opposed to Galois representations.
Right.
But yeah.
There is one other question here about how the style of training as a PhD student influenced your mathematical thinking. If there is anything in particular you could say.
Well, as I mentioned, there's advising, and then there's after PhD. So I mentioned there are a lot of different ways of advising. I mean, Tate's way of advising probably wasn't right for all students, but the students it was right for, it was really good because it taught you to do mathematics on your own. I wouldn't say I really had much in the way of postdoc advising. Michael Artin was technically my postdoc advisor at MIT. Wonderful guy, brilliant mathematician, but the way we thought about mathematics didn't mesh that well. I mean,
what were the sort of primary differences that were there?
He just knew so much algebraic geometry. I think he just didn't quite realize how little I knew. And also, he was an algebraic geometer, and I was a number theorist, and there was overlaps, but not entirely. Yeah. I don't know that I have that much more to say about that.
Fair. Yeah. So I think we are coming close to the end of the time that we had set aside. But if you have, so maybe if there's any other parting words of advice or maybe reflections that have come up in this conversation that you want to pass on before we. Could be advice to maybe to make it easier for you to have a question here, maybe we can frame it as advice for people getting into the field now, maybe early career researchers, PhDs, or early postdocs, something like this.
Okay, I'll say two things, that one of which is maybe more directly related to that, which, at least for me, I always just followed my own interest. If I found math interesting, then it was worth working on. I didn't worry too much about whether other people thought it was interesting. I hoped they would. And some things people have, and some things maybe people haven't so much, and that's fine. The other thing, which I got into later in my career, but I would encourage people to do is get involved with the math community. For example, in the United States through the AMS, in Canada through the CMS. Their conferences are good places to meet people, get to know people. The special sessions especially are a good place to get to know people in your fields.
Right.
And since I've been doing a lot with the AMS for the last couple of decades, urge people to get involved also with join committees and sort of help the general profession. Maybe not as a postdoc, But once
Right.
but even as a postdoc you can.
Right.
But certainly once you're a faculty member, you're part of this big community.
Right.
And it's really worth getting involved.
Right. I do actually have a follow-up question on the first one, on the first point you had there, about people sometimes liking the work or not. Is there any point that you can think where you were surprised in either direction, either where you published something that you thought was really going to be a hit, and then you didn't get the reception you were expecting, or conversely, a paper that you thought was just, it's some cute little idea, but then everyone, it ended up being really popular?
Well, I never expect anything I publish to be that popular, so so the first no. But the second, that can happen when something you do turns out to be of interest to a wider group than you expected, which can happen later. So one of my most cited papers is a paper on Wieferich primes and the ABC conjecture, which you probably don't want the details of. But in that article, I published a proof, because it was a corollary of the other stuff in the article, a proof actually of an exercise I had put in the original elliptic curves book, which I can even describe it. If you have an elliptic curve and you have a rational point, you look at the multiples of the point, you can ask about the primes that appear in the denominators of the coordinates. And the theorem says that once you take a big enough multiple, every subsequent multiple has a new prime appearing in the denominator.
So pause the video and try it before.
so these are called primitive prime divisors, okay? And they were known in the multiplicative group case, and this is the elliptic curve case.
Okay.
It was fun. And it turned out later that this had applications and was of interest for elliptic curve cryptography.
Oh, okay.
So that paper has a ton of references in papers on elliptic curve cryptography.
Who knew? Was that the beginning of your of thinking about cryptography, or was that on your mind before?
Well, elliptic curve crypto I'd kind of been following because I was interested in elliptic curves before there was elliptic curve crypto.
Right.
But I've certainly never been an expert in the field. I've written a handful of papers on it. No, my interest in cryptography really, we missed that whole story, but I'll be talking about some of it this afternoon, is this lattice-based crypto that one of my colleagues started thinking about, and then he recruited Jill Pfeiffer and me to help him work on it. So it wasn't elliptic curves at all, and it's not arithmetic geometry at all. It's all about lattices.
Well, so for those, I don't know if the Richard and Louise Guy lecture will be recorded.
I don't know if it's recorded, but it's live streamed.
Oh, it will be live streamed. Okay, yeah. So I will I think this video will come out after that. But if it is recorded, I'll link it in the description. But otherwise, thank you again very much for joining me today.
Thanks for inviting me to talk.
Yeah. Okay.
Okay, take care.
QED.